minutes into the class already. Yeah, got it. I'll just continue. Okay, let me go back to where was that? Okay, so yes, all right. So what we're gonna do is look at this mixture of the sodium salt, of the weak acid, and the weak acid itself. And as I was saying, the sodium salt will undergo complete dissociation, right, to form the ions. Oh, no, I forgot to share my screen. Okay, sorry about that. So, especially whoever is out there in Zoom. Okay, so as I was saying, we have the combination of a weak acid in solution and the sodium salt of the weak acid. The sodium salt will undergo complete dissociation, as you can see here, right? And then the weak acid will undergo partial dissociation, as you can see here. And in the case of the weak acid, we can write down the Ka expression, the acid dissociation constant expression, which would be the concentration of H plus times A minus over the concentration of HA. So we can rearrange this equation to solve for the concentration of H plus. The concentration of H plus will be equal to Ka times the concentration of HA divided by the concentration of A minus, right? Now, if we were to find the minus log of both sides, because remember, the pH by definition is a minus log of the concentration of H plus, right? So if we find the minus log of both sides, we're going to get this here, which will be equal to the pH, and that will be equal to minus log of Ka minus log of HA over the concentration of A minus. All right? What happened here? Okay, so we can basically break this down to, or we can express this as the log of A minus over the concentration, I'm sorry, log of the concentration of A minus divided by the log, the concentration of HA. You'll notice what I did here is that I switched these two. One becomes a denominator and the other becomes a numerator. When that happens, if you remember from your math courses, that sign here will become positive, right? If you switch these two here and here, then the negative sign here becomes the plus sign there, right? And therefore, the next step I'm going to show you is what happens as far as the minus log of H plus is concerned. That would be equal to the pH. The minus log of Ka is called the pKa. Did I introduce to you guys pKa? No? Okay, I'll explain that shortly. In fact, let me explain that now. It's not anything too complex. The pKa of an acid is equal to minus log of Ka, right? And the pKb of a base is equal to minus log of Kb, right? And there's a relationship between pKa and pKb. If you remember that Kw is equal to Ka times Kb, remember that? So if you find the minus log of both sides, you're going to get minus log of Kw, which would be equal to minus log of Ka plus minus log of Kb, right? Now, Kw, if you remember, is a constant value. It's the ionic product of water, 1.0 times 10 to the minus 14, right? So if you plug this into your calculator to find the minus log of that, and you put a negative sign in front of that, you're going to get 14.00, right? And this will be equal to minus log of Ka, which is pKa, plus minus log of Kb, which is pKb, all right? So the relationship between pKa and pKb is equal to 14.00, all right? So I thought I'd cover that, but I was thinking about it and then I realized I didn't. So that's pKa and pKb. And let me just say that if you recall, when I introduced to you guys Ka, right? Remember I said that Ka can be used to compare the strengths, you know, between two weak acids. The one with the higher Ka value would be the stronger acid. So the higher the Ka value, the greater the acid strength. And we can say something similar about Kb. The higher the Kb value, the greater the basic strength, right? But because of this negative sign here in both cases, there's a sort of inverse relationship between pKa and Ka, right? So basically, the higher the Ka value, the lower will be the pKa value, and therefore the stronger the acid, right? And something similar can be said for pKb. The larger the Kb value, the lower will be the pKb value, and therefore the stronger the base, right? So you have that sort of relationship between the strength of either the acid or base, the size or magnitude of Kb or Ka, and also the size of the value of pKa and pKb, all right? Okay, so that's a bit of an aside. I just wanted to explain, of course, in this equation, how minus log Ka becomes pKa, because that's basically what pKa is equal to, all right? So basically, this equation here can be used to calculate the pH of a solution which contains a weak acid and a conjugate base of that weak acid, all right? And that equation is has a special name. It's called the Henderson-Hasselbalch equation. Let me erase everything here, right? Which will become important as you're going to see shortly. So this is how you can express the Henderson-Hasselbalch equation. It's going to be pH is equal to pKa plus log of the conjugate base of the acid divided by the concentration of the acid. All right? So that's basically how that works. Now, there's a special name. Oh, well, before we get to that. Okay, so we can use that equation to calculate a pH of this solution right here, which is a mixture of formic acid, which is a weak acid, right? And potassium formate, which is the salt of that weak acid, all right? So as stated here, we identified as such a mixture of a weak acid and its conjugate base, right? So this is a weak acid, right? And the way it's going to dissociate, of course, initially, you're going to have 0.30 m of the weak acid. You're going to have none of the H plus, and as far as the formate ion is concerned, because this will undergo complete dissociation in water, the concentration of the formate ion is going to be 0.52. The change, we don't know what it is, but we're going to call it minus X for the formic acid, plus X for the H plus, and plus X for the formate ion. And therefore, at equilibrium, all we have to do is add the initial and change lines to get these terms here, right? And then we plug that into the Ka expression. But before we do that, we make an approximation, of course, that X is so small that 0.30 minus X is 0.30, and 0.52 plus X is 0.52. And then we plug those values into the Henderson-Hasselbalch equation. And of course, by right, you should calculate the percent dissociation. But I can confidently tell you that the percent dissociation is definitely less than 5% in this case. So all we have to do is plug the numbers in. Of course, we need to find out what the pKa value is. So of course, you'd have to go to the tables and look up the Ka value for formic acid and do minus log of that. Once you do minus log of that, you're going to get this, 3.77, right? So basically, you just plug all the numbers in, and according to the calculation here, the resulting pH of this solution is going to be 4.01, all right? So that's basically how you would calculate the pH of this solution using Henderson-Hasselbalch equation, all right? Any questions about this? Any questions? Any questions? Any questions? Okay. So let me now talk about these solutions that we're just discussing, right? We call these solutions buffer solutions, or simply buffers in some chemical literature, right? So a buffer solution is a solution which is a mixture of either a weak acid and the salt or the conjugate base of that acid, or a weak base and the salt or conjugate acid of that weak base, all right? So that's basically what a buffer solution is. And buffer solutions are very special for reasons I will get into right now, right? Basically, a buffer solution is very special because when you add a small amount of acid or base to it, the pH of the solution itself does not change by much. Now, it does change, but it changes ever so slightly compared to pretty much all other types of solutions, right? If you add a small amount of acid or base to, let's say, water, and we're going to see a graphical demonstration of that, the pH will vary widely, right? In terms of the change before and after you add the acid or base to it. But in the case of a buffer solution, the pH does not change by much. And this is very important, especially when it comes to biological systems. I don't know if you have met the concept of buffers in your biology courses, but buffers are very important. Well, certain components of biological tissues. For example, blood, right? There are buffers that exist in the blood, which basically maintains a certain pH range, right? So that, if you consume something which is acidic or basic, the pH doesn't change that much and therefore would not result in any adverse physiological effect. All right, so that's just one example. There are other examples in the human body where you have buffers performing the same role because, as you may or may not know, certain biological processes require a narrow pH range of the environment. So therefore, that's why buffers are very important. So let me get into how buffers work, right? So as I said before, what I'm going to do is focus on the type of buffers which consist of a weak base or a conjugate base and the weak acid of that conjugate base, right? So let's say you decide to add a small amount of a strong acid to the buffer, right? So the question is, how does the buffer work so as to not have the pH change by very much? Well, when the acid is added to the buffer, what will happen is that the acid will produce hydrogen ions, and the hydrogen ions will react with the conjugate base of the buffer, right? So what will happen is that initially the pH will be relatively low when you add the hydrogen ions, but because of the presence of the conjugate base, which in this case is the acetate ion, it will immediately react with most of the H plus added and form a weaker acid. And as a result, the pH will not change by much, right? So when you add a strong acid, the component of the buffer which mops up that acid will be the conjugate base, right? And therefore, it converts to a weak acid, which will have a very minimal effect on the pH of the resulting solution. On the other hand, if you add a strong base, right, which would increase the pH immediately, right, upon addition of the strong base, but what will happen is that the base will react with the acid component of the buffer, according to this equation. So this is a base, or the base will produce hydroxide ions. It will react with the acetic acid, and it will form the acetate ion, which is a weaker base, and therefore this will not have any profound effect on the resulting pH of the solution, all right? And that's basically how a buffer works, right? The buffer works by reacting with either the acid that is added or the base that is added, right? And what you need to remember is that the acid, if you're adding an acid, then the acid will react with the basic component of the buffer to convert it into a weaker base. A weaker acid. If you add a base, then it will react with the acid component of the buffer, which will convert it into a weaker base, which is the acetate ion. And in both cases, the pH will not be affected by much. All right? Okay, so that's basically an overall description, qualitative description of how buffers work. I think we're going to get into an actual quantitative example. But before we do that, let's look at this graph here. So as I said before, the buffer does not change its pH by much when you add a small amount of acid or base to it, right? That's what makes it unique compared to other solutions, right? What we're looking at here is a plot of pH versus the amount of acid that is added mole-wise to the buffer solution in one case and water, right? And as you can see, in the case of water, you're starting from here, which of course is pH 7. And if you add 0.02 moles, you see there's a significant drop in the pH from 7 to less than 2, right? And then the pH continues to fall as you add more and more acid. But look at what happens in the case of a buffer. basically it does not change as dramatically. There's a slight decrease as you continue to add your acid, but the pH does not change very much, right? And that's basically how a buffer works, all right? And you'll see a similar thing. If this was sodium hydroxide, there will be a slight increase in the pH of the buffer. In the case of water, there will be a dramatic increase in the pH of the water when you add sodium hydroxide. Okay, any questions so far? Any questions? Any questions? Okay, so let's see if you can answer these questions. Question is asking, which of the following are buffer systems, right? Now, let me remind you what we said buffers are. Buffers are mixtures of a weak acid and the sodium, or I should say the salt of that weak acid, or the conjugate base of that weak acid, right? So let's look at a mixture of potassium fluoride and hydrogen or hydrofluoric acid. So what say you? Is that a buffer system? Potassium fluoride and hydrofluoric acid in the same mixture. Will you say that's a buffer system? Yes, no, maybe so? Let's ask ourselves the question. Is hydrofluoric acid a weak acid? Yes, it is. Remember, you need to memorize those 6 weak acids I told you about, right? Hydrofluoric acid is one of them, right? And it's mixed with potassium fluoride. So therefore, that's a buffer system, right? A weak acid and the salt of that weak acid. Okay, so A is a buffer system, all right? What about B? B is a mixture of potassium bromide and hydrogen bromide. Is that a buffer solution? Is HBr a weak or strong acid? Strong, right? So therefore, by virtue of that, that mixture cannot be a buffer mixture, right? So therefore, because HBr is a strong acid, that solution is not a buffer solution. Okay, now C might not be immediately obvious, but let's look at it. Sodium bicarbonate mixed with sodium carbonate, right? Now let me give you a little hint. We can represent the carbonate ion, we can ignore the sodium ion, right? For this purpose. And therefore, we can write down CO3, 2 minus, mixed with HCO3 minus. All right? So my question again is this a buffer solution? The mixture of the carbonate ion with the bicarbonate ion. Well, which of these would you expect to be the acid in this case? Which would be the acid, the carbonate or the bicarbonate?
Bicarbonate.
The bicarbonate. All right, very good. And what type of acid do you think that is? Is that a weak or a strong acid? Remember, there are 6 strong acids. Is bicarbonate one of them? No. All right. So the bicarbonate is a weak acid, and the carbonate ion is a conjugate base of that acid. So therefore, that mixture will be a buffer solution as well. All right. So remember, by definition, a buffer solution is a mixture of a weak acid and the salt of that weak acid, or a weak base and the salt of that weak base, right? Just to give you a base example, this mixture here, NH3 and NH4 plus, right? This would be the weak base, and this would be the conjugate acid of that weak base. So that's also a buffer solution as well, all right? So that's just an example of a basic buffer solution. All right, any questions about this particular example? Any questions? Any questions? Okay, moving along. Now here's where we're going to get into a real quantitative example of a buffer solution. So in this case, actually what I just mentioned, ammonia is a combination of ammonia and ammonium chloride, right? So that's the weak base, and this would be the salt and that weak base, right? So they gave you the molarity of both of them. And it says, what is the pH after the addition of 20.0 mils of 0.050 m sodium hydroxide to 80.0 mils of the buffer solution? Let me check something here. Okay, you know what? I prefer to do this myself instead of relying on this thing here. All right. So the first thing I would do is write down it's a two-part question. Okay, so it's asking for you to calculate the pH of the buffer solution, right? So you need to calculate this first, right? And then the pH after the addition of 20.0 mils of the 0.050 m sodium hydroxide solution to 80.0 mils of the buffer solution. Okay, so let's deal with the first part first. Very simple, actually. We use Henderson-Hasselbalch. pH is equal to pKa plus log of the concentration of A minus divided by the concentration of HA, right? And then we just put the numbers in. Now, we'd have to go to the tables to find, okay, I'm not sure about this. So let me consult the tables, right? Because you'll have access to the tables to determine the pKa. So let me go there, tables. Okay, so this is the table that you'll consult. And what I will look for is, okay, they don't give you the Ka for the ammonium, but they gave you the Kb for ammonia, right? So that's 1.8 times 10 to the minus 5. So going back to this, I'm going to say that Ka is equal to 1.8 times 10 to the minus 5, right? So we're going to use that value here for pKa. So pH will equal to, according to the Henderson-Hasselbalch equation, minus log of 1.8 times 10 to the minus 5 plus log of A minus, which would be the base, which would be the ammonia, which is 0.30 m, divided by the acid, the conjugate acid concentration, which is 0.36 m. All right? So that's basically how that is set up. And now we need to do the number crunching. So I'm going to work out what's within the parentheses, 0.3 divided by 0.36. And then I find a log of that. And then I add to that minus log of 1.8 times 10 to the minus 5. Oops. Oh, you know what? Let me do this first. Let me find the minus log of 1.85, 1.8 times 10 to the minus 5. Okay, so that part is equal to 4.74. And then I'm going to add to that log of 0.30 m divided by 0.36 m. Okay, so now I can work this out. So 0.3 divided by 0.36, find the log of that, and then I'm going to add that to 4.74. So according to my calculation, the pH of this solution, before you add anything to it, is 4.66. Please check and make sure I'm doing the right thing. I think I am. Let me do another recheck. Okay, that's what I got, 4.66. Yes.
Is KB and KA like equivalent to each other?
No, remember I said that Ka times Kb is equal to Kw. That's the relationship between Ka and Kb for any acid and its conjugate base.
So you took KB, which is 1.8 times 10 to the minus 5.
Oh, right, thank you.
I was highlighting.
Thank you very much. I'm glad you pointed that out. How could I forget? So, okay. So basically, what am I gonna do? I'm going to take out this here. Oh, I can't erase it from that, sorry. Thank you for pointing that out. In fact, this value here will not be here. Okay, so what do we do is that we find KB. Oh, we're given KB, we find KA, right?
Yeah.
So KA is equal to KW, which is 14.00, divided by KB, which is PKB, which is 4.76. Sorry, KA is equal to KW divided by KB, all right? And this will be equal to 1.0 times 10 to the minus 14, divided by KB, which is 1.8 times 10 to the minus 5. That's what I should have done. Thank you. So 1 times 10 to the minus 14, divided by 1.8 times 10 to the minus 5, and that will be equal to 5.6 times 10 to the minus 10, and that goes here. So basically, you're going to have minus log of 5.6 times 10 to the minus 10, right? So when I do that, I'm going to get minus 9.25 or 9.26. So this will be incorrect here. So let me work this out now. 0.3 divided by 0.36 log, and then this should be 9.26, not minus 9.26, plus 9.26. So according to my calculations, I got 9.18. Let me just do a quick check through to make sure I'm doing everything correct. So I got 9.18. Let me erase this here. That should just be 9.26. All right. Okay, so that's a pH before you add anything to this solution, right? Now I want you to keep this number in mind here, right? The pH I will just calculate it, because what we're going to look at next is how the pH changes when we add the sodium hydroxide. All right. Now I'm going to need a space, so what I'm going to do is erase everything. How do I get rid of this? Oh, let me leave that there. All right. I'm going to need that anyway. Okay, now we have to ask ourselves the question: what happens when we add the sodium hydroxide to this mixture? Well, as I said before, when you add a base to a buffer mixture, the base is going to react with the acid part of the buffer, right? So what's going to happen is the base is the sodium hydroxide, so the hydroxide ions from the sodium hydroxide will react with the acid part, which would be the NH4 plus, right, of the buffer. So therefore, when this reaction takes place, you're going to end up with ammonia plus H2O, all right? So what we need to do first is find out how much ammonium and ammonia and base that is present initially, right? Now, how do we find that out? Well, we have to do some calculations here. Let me see if I can do it. Let me draw a line here so I can do it by itself. Okay, first thing we need to find out is the number of moles of OH minus added. right? They gave you the volume and they gave you the molarity, right? So the number of moles of the hydroxide ion would be 20.0 mils, which we have to convert to liters, 1 liter over 1,000 mils. And then we multiply that by the molarity, which is 0.050 m, right? So when we do that calculation, 20 times 10 to the minus 3 times 0.050, the answer I got is 1.00 times 10 to the minus 3. So that would be the moles of sodium hydroxide that you're going to have initially right here, 1.00 times 10 to the minus 3, right? Then we do a similar calculation for the ammonium chloride, right? Now, according to the question, 80 mils of the buffer is what was used, right? So basically, the number of moles of the ammonium will be equal to 80.0 mils. Again, we convert that to liters, 1 liter over 1,000 mils. And we multiply that by the molarity of the ammonium, which is 0.36 m, right? Let's see what that gives. 80 divided by 1,000 times 0.36. And I got, when rounded off to a 3 sig figs, I got 0.0288 moles. All right? And then we need to find the number of moles of ammonia. How do we find that? Well, we're going to use the same 80 mils because that's the volume of the buffer which contains ammonia. Convert that to liters, 1 liter over 1,000. And then we multiply by the molarity of the ammonia, which is 0.30 m. All right, so I'm sorry, this should be rounded off to, what did I say? 2 sig figs. So this should be 0.029 moles, right? This is 1.0 times 10 to the minus 3. So the ammonium would go here, 0.36. And I just realized something. This should be actually to 2 sig figs. So instead of 1.0, this should 1.00, it should be just 1.0. So just take out that 0 here. And as far as the ammonia is concerned, initially you're going to have 0.30 moles, right? So these are all mole values, right? Now, in this case, it's an acid-base reaction. It's not going back and forth, right? In other words, the reaction will go in one direction. And as we all know, in such reactions, the limiting reactant will be the one that's used up, right? And you can tell easily which of the reactants will be limiting. It would be the hydroxide ion because it's a 1-to-1 ratio between these two. And because this is lower than this will be the limiting reactant. So what that means is that as far as the change is concerned, all of this will be used up, minus 1.0 times 10 to the minus 3. The change here, because, oh, I'm sorry, yes, ma'am.
Shouldn't the mole for the NH4 be the 0.029 mole and not?
Oh, yes.
For the NH4?
Yeah, it should be, yeah, thank you. Thank you again. At least it shows you're following, my dear. Okay, 0.29. Okay. So as I was saying, the change here is minus 1.0 times 10 to the minus, yes, sir.
Still gotta calculate the moles for the NH3. Right, or
Oh, that's the reason why, okay. So 80 divided by 1,000. That's the reason why I put 0.30 there. Divided by, or multiplied by 0.3. So this should be 0.24, which means that this here should be 0.24. Thank you guys for picking up on all these little errors that I'm making.
0.024.
Yeah, 0.024, yeah, thanks. Thank you very much. Okay, so this should be 0.024. Okay, so and this should be 0.029. I'm making mistakes all over the place. This here should be 0.029 moles, right? Okay, so as I was saying, and this should be 0.024. Okay, so as I was saying, this is the limiting reactant. All of this will be used up. So therefore, the change as far as the ammonium is concerned would be minus 1.0 times 10 to the minus 3. And the change as far as the ammonia is concerned is plus 1.0 times 10 to the minus 3. All right? And then we calculate what happens at the end of the reaction. So obviously this will be 0. And then as far as the ammonium is concerned, that will be 0.029 minus 1 times 10 to the minus 3. And that would be 0.028. And then as far as the ammonia is concerned, 0.024 plus 1 times 10 to the minus 3, that's going to be equal to 0.025. 0.025, right? And then what we need to do at this stage is calculate the concentration of both the ammonium and the ammonia and plug them into this equation. Now, how do we calculate that? Well, remember, you're mixing 20 mils of the solution of sodium hydroxide, with 80 mils of the buffer solution, which means that the final volume is going to be 100 mils, right? So let me just write here that total volume is equal to 20.0 mils plus 80.0 mils, and that will be equal to 100.0 mils, which we have to convert to liters because we'll be calculating the molarity. So that will be equal to 0.1000 liters, right? So the concentration of the ammonium would be equal to the moles, which is the 0.028 moles, divided by 0.1000 liters, and that's going to be equal to 0.028 divided by 1,000. So that's going to be equal to divided by 0.1. What am I doing? 0.038 divided by 0.1. That's going to be equal to 0.28 M, and the concentration of NH3 will be equal to 0.025 moles divided by 0.1000 liters, and that will give 0.25 M. So now we have the molarity of the ammonium, we have the molarity of the ammonia, and we can plug those values into the pKa expression. Where am I going to fit this? Okay, let me do this here. See if I can squeeze this down here. So pH is equal to the pKa, which is minus log of the 1.8 times 10 to the minus 5. Plus log of the conjugate of the concentration of the base, which is 0.25 M, divided by the concentration of the acid, which is 0.28 M. And then we work this out. Now, if I remember correctly, this part here works out to 4.76, right? Plus, let me see what that part works out to. So this would be, yes, ma'am.
You're still using the KB value. The 1.8 times 10 to the minus 5 is the KB value.
Damn it, thank you. So the KB value, if I remember correctly, was 5.6 times 10 to the something, right? 5. 5.6 times 10 to the minus 10? All right. Thank you. So let me erase this again. Okay, so 5.6 times 10 to the minus 10, log of that, which is 9.25. And then I'm going to add to that 0.25 divided by 0.28, log of that, and this part works out to be equal to minus 0.049. And then I add that to the 9.25, and I got 9.20. All right. Now, if I remember correctly, the previous pH was 9.17, right? Before you add anything, right? That's what we calculated earlier. So this is before, and this is after. And as you can see, the change is very small, right? 9.17 to 9.20 after addition of base. So that's a pH change of 0.03 units, very small, right? And that basically demonstrates how a buffer works. The pH does not change by much when you add a small amount of acid, or as in this case, base to a buffer, all right? So that's basically how that is done. All right, any questions about this particular example? Any question? Any questions? All right, what I'm gonna do now is, what time is it, by the way? Ooh, having so much fun. Let me pull up assignment number 5. Okay, let me publish it first. For those of you, and I think I have some copies of assignment number 5, so I might as well give it to you now. Where is it? Where is it? Where is it? Where is it? Okay, here it is. Take one press down. That's for you. That's for you. That's for you. And for you. Oh. Sorry. Okay, so for you guys out there in Zoom, I'm going to publish it right now, and I'm just going to bring it up on the screen so we can look at question number 1. Let me see what questions we can do. Yeah, we cannot do question number 2 yet because that has to do with titration. Okay, the only question we can do so far, as far as I can see, is question number 1. Okay, so question number 1, let me bring this on the screen here. It says calculate the pH of a 0.25 m. Oh, no, we can't do, this is not a buffer solution. Looks like I did not include any buffer solution questions. Let me just check this here. Okay. All right, looks like I did not, I think I have to create an addendum to this so that you can do, get some practice doing buffers. So we won't be able to do any questions from this. However, come to think of it, in assignment number 4, as I said before, let me bring that up here. In assignment number 4, there's one question which you would not be able to do up until now, and that is question number 17, the C part, all right? Now the question says, calculate the pH of a solution that results when 40 mils of 0.10 m ammonia is, and then in the case of the C part, mixed with 20.0 mils of ammonium chloride. All right, so basically, you're taking 40 mils, 40.0 mils of ammonia, of 0.10 M ammonia, and you're mixing it with You're mixing it with 20. You're mixing it with 20.0 mils of 0.200 M ammonium chloride, all right? So this would be a buffer solution again, because you have the ammonium, which is the conjugate acid of ammonia, right? So what I would do is, I would find the moles of each of them. Number of moles of ammonia would be equal to 40.0 mils, which you have to convert to liters, 1 liter over 1,000 mils, times 0.100 M, right? And what does that give? 40 times or divided by 1,000 times 0.100. And that gives you, according to my calculations, 4.0 times 10 to the 4.00 times 10 to the minus 3 moles. And then I do a similar calculation for the ammonium, NH4 plus, right? And the volume for that is 20.0 mils, which I'm going to convert to liters, 1 liter over 1,000 mils, multiplied by its molarity, which is 0.200 M, right? So when I do that calculation, guess what? That's also equal to 4.00 times 10 to the minus 3 moles, right? Now, they said that the initial volume was 40 mils of the previous solution, and you're adding 20 mils to that, so the total volume is equal to 60.0 mils, right? Now, here's the thing. Normally, I would require that you calculate the concentration of each of these, but guess what? Because this is the same as this, right? If we go back to the Henderson-Hasselbalch equation, pH is equal to minus log of, of the Ka, or, I'm sorry, pH is equal to pKa plus log of concentration of A minus over HA. Because these two are the same, that means ultimately the concentration of A minus and HA will be the same, right? So these two will cancel each other, so you're going to end up with log of 1. And what is log of 1?
0.
0, exactly. So basically, the pH would be equal to the pKa of the acid. So all we have to do is find the minus log of the Ka of the acid. So, of course, we know that the Kb is equal to 1.8 times 10 to the minus 5. So, and we found out that the Ka from the example that we worked on a PowerPoint is equal to 5.6 times 10 to the minus 10, right? So the pKa is equal to minus log of 5.6 times 10 to the minus 10 minus log, which I think we did that already. What was it? 5.6 times 10 to the minus 10. I'll do it anyway. 9.25. 9.25, right? So this would be equal to the pH of the solution, and that answers that question. All right? So at least we have one example of a buffer question, but that was not in the current assignment I gave you. That's from assignment number 4, unfortunately. I'm going to see if I can find some more buffer questions and include that in assignment number 5. But for now, That's pretty much it. All right, any questions about this one? Any questions? Okay, so that's pretty much it for today. And I guess, let me see, did I get everybody's attendance? Let me check. Let me see who, Ronnie is not here. Gilcrease, that's you. The CS is here,
Yes.
okay. And Renfro, Salvador, okay, that's it. All right, so that's it for today, folks.
Let's see. That still stays in. So she told me not to distribute from here. She said it's more. I changed it to a product.
Okay, what's the question? What is the question that we got?
You know, it's like only a half a point, but it's like really bugging me.
Okay, for the first ionization of phosphoric acid with water, so where is it? Okay, that's correct. Mhm.
But it's still.
Yeah, right. All right. Mhm.
Is if the KA1 come in,
For which one?
KA1 was water.
I was like, there's
Right.
no way. I'm like,
Oh, so you're asking about KA1? Well, that's basically the concentration of this times this divided by the concentration of that. Oh, let me see.
Against the other guy.
Depending, and I think that would be the case here,
That was free.
right? So therefore, as a result, this would be the concentration of H3O plus, and then you can find the pH based on that. Yeah, that's what I said, right? Okay. So they're saying that this is equal to this.
I'm like,
Exactly.
this, I
So the pH
Cause I
minus
drew
log
it.
of,
So I
yeah,
drew
whatever that
it.
is.
So I gave
And I
you.
didn't, but I didn't know that.
Verbally look at.
Exactly, right.
And I solved it.
Mhm. You ever see?
I was like, the two goes away, goes there again. And then she explained it in class.
That's how you do that.
It's so crazy. I was like, looking at her, and she did it in the end. There's like your brain, she had like almost like scribble marks on her pages.
No, you can't do the question in this.
Like I need
Yeah,
to start doing
not yet.
it
I need to
in
add some buffer solution questions to that. Mhm.
And then. I did click this down.
For which one?
15.
15? Oh,
That was for the two athletes.
okay, so what was the percentage? Oh, they were both less than 5?
0.20. And I timed that by.
Right,
100, and I got 0.0.
Okay, if that's the case, then that means you can use the X values that you get in each case and add them together
And that's what I did.
and then okay, good, right, okay. Yeah, as long as you show, I think this is yours.
And then for C was 17, it did turn out to be 9.35.
Yeah, mhm, yeah. What's up, sir?
I have a question about the attendance. Is that part of the final grade?
No, typically, the only reason why I do attendance is because at the end of the semester, when I'm entering the grades, For those students who get D or below, I have to enter the last date of attendance. So that's the reason why, it's not contributing to your, to your grade.
Because I came in late to a couple of Zoom ones on Mondays.
Yeah, the Zoom keeps a record of your attendance as well, so.
Oh, okay. Thank you.
Okay, so Mr. Lackey, I'll be signing off. Right